In this video, we are going to study more about partially ordered sets, mainly to give some more terminology for homework problems and for later problems in this section, and to give the notion of Poset isomorphism. And so if you've taken Algebra 2, you've actually seen this before in an area of math called Galois theory, where there's this fundamental theorem that any field extension of any subfield of a field extension corresponds to a certain subgroup called the Galois group, and there's sort of a reverse bijection between these two sets, and that's called the Poset isomorphism. First, here's a poset. A K multichain is a sequence of K symbols, elements that are pairwise comparable in your poset. So for instance, this identity permutation is less than or equal to itself, is less than or equal to the transposition 1, 2, it's less than or equal to the 3 cycle 1, 2, 3. This is a sequence of length 4, it's a 4 multichain. And we call it a K chain if all the inequalities are strict. So we had to remove this E here, and now we have a 3 chain. And so in general, an N chain is going to be either a set of n pairwise comparable elements in a poset, or sometimes it's also used to denote a specific poset that only has n elements written in increasing order. So let's fix a favorite poset P. An element in P is called minimal if whenever any other element is less than or equal to it, it's actually the element itself. In other words, there's nothing less than m, strictly less than m. Similarly, another element is called maximal if there's nothing strictly bigger than it. So for anything that's at least as big as it, it's itself. So for instance, in this poset down here, these two elements are maximal because there's nothing above them, and this element is minimal because there's nothing below it. And so this is in contrast to the usual notions we use in mathematics of minimum and maximum. So sometimes this distinction pops up in certain arguments. If you see the word maximal or minimal, it means there's nothing smaller than it. Minimum means the other notion we're used to, everything is bigger than it. And oftentimes if a partially ordered set has a minimum element, we denote it 0 with a hat, always. So whenever we see 0 with a hat, that means it's the minimum element. And so 0 is minimum if for every other element P, 0 is smaller than P. Similarly, 1 is a maximum element if every other element is below it. So for instance, this element is a minimum because everything is above it. On the other hand, there is no maximum element in this poset, because while this element is maximal, these two are not comparable. So this condition is not met for this element, and is not met for this element either. And everybody else has at least something above it. So a nice example of a proof using partially ordered sets in these notions is that an element is maximum. So P has a maximum element if it has only one maximal element. As you can tell, the maximal element is it. Similarly, 0 is minimum if P has only one minimal element. So these two words are related. And so let's prove just this second line. So suppose you have a minimum. I want to actually claim that is a minimal element. And so how would I do that? Well, I check the definition. I let P be an element less than or equal to 0. And I want to show that P is equal to 0. But since 0 is minimum, we know that in fact we have that 0 is less than or equal to P. And since the partial orders are antisymmetric, then we see that P is equal to 0. And so that tells you that in fact we've satisfied the condition for 0 to be a minimal element. So 0 is minimal. And what we need to claim is it's the only minimal element. So how do we do that? We take another minimal element. Well, since 0 is minimum, we know that 0 is less than or equal to m. But since m is minimal, nothing is below it. That tells you 0 has to be equal to m. So starting with an arbitrary minimal element of our poset, we showed that it's actually the element 0. So this tells us that not only is 0 minimum, it's the only minimal element. And that's all we needed. And so what have we shown? We've shown that if your poset has a minimum element, then that minimum element is minimal and it's the only one. Now you need to go backwards. Suppose you have only one minimal element, and I'll argue that it's a minimum. Or more accurately, take the contrapositive of the converse statement. So the converse statement would be, suppose your poset has only one minimal element, show that it has a minimum. The contrapositive would be stating that suppose you don't have a minimum, then you must have two minimal elements. So one thing that's worth pointing out is that every poset must have a minimal element, and that can be, or at least a non-empty poset must have a minimal element. And why is that? We'll take an arbitrary element. If it's not minimal, then by definition of that minimal, there's something strictly less than it. Then look at that new element. If it's not minimal, there's something strictly less than it. And if you continue, you're going to have an infinite decreasing chain, but you have a finite poset, so eventually the chain has to stop, and the element it stops at is a minimal. And so we can guarantee that you have to have a minimal element. I should call it M. Now, how do we know that there's more than one minimum element? So we know M is not minimum. And so by the negation of this statement, that means there exists a P such that it's not the case that M is less than or equal to P. Well, what does this mean? This means either that P is less than or equal to M, or P and M are incomparable. However, we can already rule out this option because we're assuming M is minimum. So if P is less than or equal to M, then P is equal to M. But then that contradicts this assumption. So we must have this case. And so in particular, you can talk about a new poset. P is incomparable to M. And we know this is non-empty. And moreover, given any two elements in here, that we take the same partial order that they had before as elements of P. And so this is a partially ordered set. And I already claimed every partially ordered set has to have a minimal element, so it must have a minimal element. Say M prime, and in particular, by definition, that M prime is different from M, so you found at least two minimal elements. So that proves the converse. And you can even see this in action here, at least if you work with maximals instead. Take this maximal element. We said it wasn't maximum because there are elements that aren't comparable to it, namely this one. So this point by itself forms the poset Q. And it has a maximal element, namely itself, and so you see you have two maximal elements. And so this really is an if and only if. And so here's an example of a type of proof you see in the theory of partial orders when you're not working just about structure results, so nothing with counting. Now we discuss how to construct new posets from old ones. And so the first operation, given two posets whose intersection is empty, we form a new poset on their union called the sum of the two posets. And how do we do the partial order? Well, given two elements in P that where x is less than or equal to y in that poset, we define x to be less than or equal to y in our new poset. Similarly, given two elements in Q that are comparable in Q, we define x and y to be comparable in P plus Q. And then we don't add any new relationships. So basically, these are two different groups, and we've just decided to put them in the same room. And so the Hosta diagram looks like that. You draw the Hosta diagram for P, then you draw the Hosta diagram for Q, and then you do nothing else. There's no new relationships between elements of P and elements of Q. The more interesting construction is a product. So the product is a partial order on the ordered pairs of the sets P and Q. And so given elements P and P prime in the first set, so first coordinates, and given two second coordinates, Q and Q prime, we say PQ is less than or equal to P prime Q prime if and only if the inequality is satisfied for the first coordinates and the second coordinates. And so here's an example. The product of these two chains is this poset. You see coordinate-wise, 2 is bigger than 1. Coordinate-wise, 2 is bigger than 1, and 4 is bigger than 3, and so on and so forth. On the other hand, we see there's no way to compare 2, 3 with 1, 4, because while the first coordinate over here is bigger than the first coordinate here, and the second coordinate, this one's bigger than that one. And so you don't have the inequalities going the right way in both coordinates, so these two are incomparable. As a more larger example, let's look at this product of a 3-chain, a 2-chain, and a 2-chain. You see that these two chains forms a diamond, but then this diamond corresponds to fixing the first coordinate as 1. You can also fix the first coordinate as 2, that gives you a second diamond. Or you can fix the first coordinate as 3, and that gives you this third diamond. In general, that's one way to draw the poset. You draw multiple copies of this second poset, one for each vertex in the first poset, and then you just connect edges like so. And right now I didn't pay attention to the labeling, but notice this labeling is kind of nice. It's done in such a way that, well, here's the 1, 2, so that instead of talking about coordinates, I could just multiply the numbers together. 4 times 3 times 5 is 60. And you see this is the divisor poset, the set of divisors. So I haven't introduced this yet, but it's the set of divisors partially ordered by divisibility. And you see that there seems to be a relationship between these two, writing the divisor poset as a product of chains. And one of the goals of the video is actually proving that you can always do this. Only we can't write equals, it should be isomorphism. Now we need to talk about what it means to be order preserving. So the right type of structure preserving maps for partially ordered sets is this one. We say that a function is order preserving if given any 2 points in the domain, such that P is less than or equal to P prime, f of P is less than or equal to f of P prime. In other words, you preserve the ordering, hence the name. For instance, here's this collection of subsets of 1, 2, 3. It's a partial order under inclusion. Here's the Hosta diagram. You can define, so in general, this map works for the power set of any set to the integers 1 through the size of the set, given by sending f of s to the size of s. And you see, so in particular, these singletons are sent to 1, these sets of size 2 are sent to 2, and this is sent to 3. And in general, this is a fact we know, is that if A is a subset of B, then the number of elements in A is less than or equal to the number of elements of B. So it's an order-preserving map. As another example from calculus, any increasing function from R to R will work, is order-preserving. An example is e to the x. So remember, a function in calculus is increasing if whenever a is less than or equal to b, f of a is less than or equal to f of b. So order preserving is just a generalization of being increasing. There's also a notion of order reversing where this inequality goes the other way, and that would be the generalization of decreasing. The only thing that makes things different here is that we don't put any requirements on what happens with incomparable pairs. So here these two incomparable pairs get sent to the same element, but it is in fact possible to define maps where they get sent to different things. Finally, what does it mean for a poset to be isomorphic to another one? We say two partial orders are isomorphic if you can find an order-preserving function between them that's a bijection, so one-to-one and onto. And so our two of our favorite posets is the end chain and the divisors poset under the divisibility relation. And something that we know from number theory or elementary school is that every number factors uniquely as a product of powers of primes. And so suppose this is such a factorization. In particular, these are distinct primes. You have pi is not equal to pj for I not equal to j. And it turns out this divisor poset is isomorphic to a Cartesian product of chains. Each chain is of length ai plus 1. Similarly, the power set of the set of subsets, so this is the collection of subsets of the integers 1 through n, is isomorphic to the product of n copies of the 2 chain, which you could have seen before if you ever actually tried this construction. A diamond times that, and look, you get a box, which happened to be the picture we drew before for the poset. So how does the proof go? Well, take a divisor of n by the prime factorization fundamental theorem of arithmetic. It factors uniquely as a product of primes. In fact, actually, it has the exact same prime factors as n, only in order to get things right, you might have to allow one of the exponents to be 0. So it has some sort of factorization into factors, powers of p1 through pk, the same prime divisors of n, where the powers range from 0 to ai. And that's because, for instance, if this were 2, if the power of 2 dividing d was larger than the power of 2 dividing n, then d doesn't divide n. That's a consequence of Euclid's lemma. And so how do we define the map? Well, given this divisor, we just send it to this sequence of exponents in order. And it's clear that this is in fact a bijection, because given such a sequence, we can create a number by doing pi to the di and taking that product over all I. And it's a theorem from the fundamental theorem of arithmetic that you have to get a bijection when you do that. That if I do this decomposition, it's unique up to ordering of factors. And here I've fixed the order of the prime numbers that we're using. In fact, actually, I can make this even more precise. We can insist that the primes are written in increasing order, and then it is in fact a bijection. Now we can go the other direction. Now, well, I still need to show that this is order preserving. I've only claimed it's a bijection. So why is it order preserving? Suppose we have two divisors of n, d and e, such that d divides e. I've already factored d, but e also factors as a product of primes. Notice, of course, since d divides e, this means that we should be able to write e as an integer times d. This is just a fancy way of writing d. And so since this is true, the powers of pi appearing in these two expressions has to be the same. So it tells you the power of pi appearing in q has to be ei minus di. So that when you do ei minus di plus di, you get ei. So in other words, if you actually look at the powers of pi, you know on one expression it has to be EI. On the other hand, you know it has to be whatever it is for Q plus whatever it is for D. And so then you see that the power, when you factor Q, has to be EI minus DI. In particular, since these are integers, this tells you that these must be positive numbers for all I, which tells you that these powers up here, EI, have to be at least DI for all I, which means that the ith coordinate of f of D is less than or equal to the ith coordinate of f of E for all I. So by definition of Cartesian product, f of D must be less than or equal to f of E. And then I already pointed out what the inverse of this bijection is. Given one of these k tuples of numbers, you just let B be the number where you raise pi to the bith power and take the product. And so right now this is just a consequence of the fundamental theorem of arithmetic, but in a later lecture we'll see why this isomorphism is useful for proving theorems. Similarly, we're going to use that in this case. Here's the power set. So I want to show that the power set is isomorphic to a product of chains. What do? Given a subset S and an integer I define delta I of S to be 1 when I is in S and 0 otherwise. And then I send this to a tuple, delta 1S dot 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 all the way delta NS. It's worth pointing out that this is really the same thing as the bit string that we've studied before, where the ith entry of the bit string is 0 when I is not in the set and is 1 when it is. And so this is the definition of our function. It turns out this is a bijection because we are just talking about bit strings. So you do know what the inverse is. You define the inverse. Given one of these sequence, you define the set to be the correspond to the coordinates where the entry of that coordinate is 1. So all I need to show is that this is in fact order preserving. We'll let S be a subset of T. Then for an element in S, delta x of S is 1. But since S is a subset of T, X is an element of T, and so delta x of T is also 1. And so that tells us that the ith coordinate of F satisfies the right inequality when I is an element of S. What if X is an element of T take away S? Well then, since it's not an element of S, this function is 0, that coordinate is 0. That coordinate is 1, but 0 is less than 1, so there isn't a problem. And when X is not even an element of T, then it can't be an element of S either, and so both these functions are 0. And so you see, coordinate by coordinate, one of these three, either you have an equality or a strict inequality. And so since each coordinate in this point in this string is less than or equal to the corresponding coordinate in this string, by definition of Cartesian product, we have the inequality as well.